All right, let's talk about rational functions. And let's begin with the definition of vertical and horizontal asymptotes. So the line x equals a is a vertical asymptote of the function if y goes to either positive or negative infinity as x gets closer to a particular number from either the left or the right. Let's look at some specific examples. All right, let's start with f of x equals 1 divided by x minus 3. It has a vertical asymptote at x equals 3. So when the numbers get closer and closer, when x gets closer and closer to 3 from below, so numbers slightly less than 3, then the y values go to negative infinity. If you were to plug in numbers closer and closer to 3 from the positive direction, meaning numbers slightly greater than 3, then the y value approaches positive infinity. And if you noticed that the vertical asymptote is where the denominator equals 0, then that would be no coincidence. That's exactly why we have a vertical asymptote at x equals 3. Let's look at another example. All right, f of x equals 1 over x plus 5 times x minus 2. So before we look at the graph, can you guess where the vertical asymptote or asymptotes may be? If you guessed negative 5 and positive 2, you're correct. So f of x has a vertical asymptote at x equals negative 5. So it goes to positive infinity if you approach from the left, and goes to negative infinity if you approach negative 5 from the right. And the opposite for x equals 2. If you approach positive 2 from the left, it'll go to negative infinity. If you approach x equals 2 from the right, it'll go to positive infinity. Let's look at another example. All right, f of x equals 1 over x plus 2 squared. Do you think this function will have a vertical asymptote? And what do you think the squared will do to the graph? So take a moment and ponder that. If you guessed that f would have a vertical asymptote when x is equal to negative 2, you would be correct. And what does the squared do to the graph? Well, you'll notice that this vertical asymptote has the same sign on both sides, because when you square a negative, it becomes positive. So we saw similar things with polynomial functions when one of the factors has a multiplicity of 2. All right, let's look at horizontal asymptotes. All right, the line y equals b is a horizontal asymptote of a function if the y value approaches the constant b as x approaches infinity or negative infinity. So we're looking at the function when x goes to infinity on the right and x goes to negative infinity on the left. Let's look at some examples. Before I show you the graph, do you think this function will have a vertical asymptote, and where do you think that will be? If you guessed negative 10 over 3, you would be correct. And what happens when the numerator is equal to 0? If you guessed that that would be a an x-intercept, you would be correct. So that's where the graph crosses the x-axis. Now let's look at the graph. So just like we predicted, the function has a vertical asymptote at x equals negative 10 over 3, which is where the denominator equals 0. And it crosses the x-axis at x equals 1/2, which is where the numerator is equal to 0. This function has a horizontal asymptote of 2/3. So when x goes to positive infinity, it approaches y equals 2/3. And when x goes to negative infinity, the value of y approaches 2/3. Is there anything about this function that might give you that horizontal asymptote? And if you noticed the ratio of the leading coefficients is 2/3, you would be correct. That's why the horizontal asymptote is 2/3. We'll talk about the rule in a few minutes, but before we do that, let's look at another example. All right, so let's look at this example, and I would definitely hit the pause button and ask yourself 3 questions. Are there going to be any vertical asymptotes? Where would they be? Will there be an x-intercept? And where will that be? And do you think this function will have a horizontal asymptote? And can you guess what that would be? Right, if you guessed that it would have a vertical asymptote at x equals 7 over 3, you would be correct. And that's because 7 over 3 is where the denominator equals 0. If you guessed that it would have an x-intercept at x equals 4/5, you would be correct. And that's because that's where the numerator is equal to 0. And this function has a horizontal asymptote of y equals 5/3. All right, let's talk about why that's the case. All right, how do we find asymptotes of rational functions? This is also called the end behavior of a function. And you'll recall we did look at the end behavior of polynomial functions. Polynomial functions, the ends either go in opposite directions or in the same direction depending on the degree of the polynomial. Well, when you have rational functions, it depends on the degree of the numerator relative to the degree of the denominator. So there's 3 cases. If the degree of the numerator is smaller, there's one possibility. If the degree of the numerator is equal to the degree of the denominator, that's another case. And if the degree of the numerator is bigger than the degree of the denominator, that's a third case. So the previous 2 examples we looked at, the degree of the numerator was equal to the degree of the denominator. And if the degree of the numerator is equal to the degree of the denominator, then you get a horizontal asymptote of y equals c, where c is the ratio of the leading coefficients. And we'll do another example of that. All right, if the degree of the numerator is smaller than the degree of the denominator, then you get a horizontal asymptote, which is equal to 0. And we'll do an example of that. And if the degree of the numerator is greater than the degree of the denominator, we get what is called a slant asymptote, meaning the end behavior is that f of x gets closer and closer to a particular function. And how do we find that function? By using polynomial long division. We'll do an example of that. So suppose f of x is x minus 3 divided by x minus 4 times x plus 2. What is the end behavior? Well, the degree in the numerator is 1. The degree in the denominator is 2. If you multiply this out, you'll get x squared. So this is our first case. It'll have a horizontal asymptote of y equals 0. All right, will this function have any x-intercepts? If you said x equals 3, you would be correct, because that's where the numerator is equal to 0. Will this function have any vertical asymptotes? Well, if you guessed that yes, it would have a vertical asymptote at x equals positive 4, because it makes this factor equal to 0, and x equals negative 2, because it makes this factor equal to 0, you would be correct. So since we've done all this work, we might as well draw the graph. So I'll put some of this information in to start. All right, so this rational function has 3 linear factors. So there are 3 places where the sign of this entire function can change from positive to negative. Either at x equals negative 2, x equals 3, or x equals positive 4. I know that 2 and 4 are going to be vertical asymptotes, and 3, 0 is an intercept. I know the horizontal asymptote is y equals 0. So the rest of it we can just fill in using a sign chart. So we just test a point in each of the 1, 2, 3, 4 regions. So if x is less than negative 2, all right, so I'm writing my original function down here just so we can see the graph better. All right, let's plug in any number less than negative 2, like negative 5. And remember, we don't need to know the exact number, just whether it'll be positive or negative. So if I put negative 5 in here, it'll be negative, negative 5 in here, negative, negative 5 in here will be negative, negative divided by negative is negative. So it has a horizontal asymptote of y equals 0 until it gets here to this vertical asymptote of x equals negative 2. So because it's negative, it's going to y equals negative infinity. All right, let's check the sign in this region. So we'll plug any number between negative 2 and 3, like 0. If I put 0 in here, it'll be negative. This will be negative. This will be positive. So the whole thing will be positive. So we have a vertical asymptote, which will go to positive infinity. And then it connects to this intercept. All right, between 3 and 4, like 3.5, this will be positive. This will be negative. This is positive. So the whole thing will be negative. I have a vertical asymptote here, but it's negative, so it'll go to negative infinity. And then test any number greater than 4, like 5. So put 5 in here, that'll be positive. This will be positive. This will be positive. So I have a vertical asymptote, so it'll go to positive infinity. And then a horizontal asymptote of 0. All right, let's try another one. All right, let's look at this example. And does it have any asymptotes horizontal or vertical? And does it have any intercepts? So why don't you take a moment and just draw a rough sketch of this function. All right, so this function will have a vertical asymptote where the denominator is equal to 0. So it'll have a vertical asymptote at x equals negative 7/2. To find intercepts, we set the numerator equal to 0. So this function will have an x-intercept at x equals 5/3. All right, and what's the end behavior? Does it have any horizontal asymptotes? And the answer is yes. And because the degree of the numerator is equal to the degree of the denominator, we'll get a horizontal asymptote that's equal to the ratio of the leading coefficients. So it'll have a horizontal asymptote of 3/2. So let's take these three pieces of information and put them in our graph and use the signs to fill in the rest. Let me get started. All right, so there are two factors, and that means there are only two places where the sign of this function will change. That will be at either negative 7/2 or 5/3. So we have three regions to check. So if I plug in a number less than negative 7/2, like negative 10, I'll get a negative divided by a negative, which is positive. So my function has a horizontal asymptote of 3/2, and then a vertical asymptote at x equals negative 7/2. And since it's a positive number, that'll go to y equals positive infinity. Then we plug in any number between negative 7/2 and 5/3, like 0. The numerator will be negative. The denominator will be positive. So the whole thing is negative. So I have a vertical asymptote, so that'll go to negative infinity. And then we have an x-intercept. All right, let's plug in a number greater than 5/3, like 10. We put 10 in here, that'll be positive. This will be positive. So the whole thing will be positive, but it gets closer and closer to 3/2, which is our horizontal asymptote. All right, let's do another. All right, let's look at this function. Does it have any intercepts? And does it have any asymptotes? All right, if you guessed that it had x-intercepts at 4 and negative 2, you would be correct. Does it have any vertical asymptotes? Right, the denominator is 0 at x equals 1, so it has a vertical asymptote. What do you think will be the end behavior of this function? Well, the degree of the numerator is greater than the degree of the denominator, so it will have a slant asymptote. How will we find the slant asymptote? Well, we'll use long division. So I'll multiply this function out so we can divide it. And we'll use long division. You can either use synthetic division or regular long division. All right, so I'm going to divide x minus 1 into x squared minus 2x minus 8. What do I multiply x by to get x squared? That'll be x. Don't forget to subtract the whole thing. So negative 2x and positive 1x make negative x. What do I multiply x by to get negative 1x? It'll be negative 1. All right, so my function could be rewritten as x minus 1 plus negative 9 over x minus 1. All right, so this part is a rational function where the denominator, the degree of the denominator is greater than the degree of the numerator. So this part will get closer and closer to 0. And my slant asymptote will be to the function y equals x minus 1. All right, let's put all this together and draw the graph. All right, so I plotted my two x-intercepts, my vertical asymptote, which is at x equals 1, and then I drew my slant asymptote, which will be the end behavior. So I don't worry about the slant asymptote here in the middle, just at the ends. All right, I have 3 factors. There's 3 places where the sign could change. So that means I have 1, 2, 3, 4 regions to check the sign. All right, let's plug in a number less than negative 2, like negative 4. So this one, oh, I drew my. All right, so if I plug in a number less than negative 4, like negative 8, this will be negative, this will be negative, this will be negative, so the whole thing will be negative. So negative up until here, which is my x-intercept. I have a slant asymptote, so it'll be asymptotic to the line x minus 1 until it gets to the x-intercept. All right, let's plug in a number between negative 2 and 1, like 0. So this will be negative, positive, negative. So the whole thing will be positive, and it gets closer and closer to this x vertical asymptote. So like that. Okay, not my best drawing. All right, let's check the numbers between 1 and 4, like positive 3. If we put positive 3 in here, this will be negative, this will be positive, and this will be positive. So the whole thing's negative. So I have a vertical asymptote, and then it goes to our x-intercept. And then when x is greater than 4, this will be positive, 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 and get closer and closer to our line. I'm going to fix that whole thing. All right, sorry about that. I just wanted to make sure our graph was beautiful. It's not going to have any corners. Let's do another example of a function that has a slant asymptote, and we'll just find the asymptote. All right, what's the end behavior of x squared minus 9 over x plus 2? Well, if you said slant asymptote, would be correct. Okay, let's find the slant asymptote by dividing. Now, there's no x term, so we need to put a placeholder in. And then what do I multiply x by to get x squared? It'll just be x. And then subtract. What do I multiply x by to get negative 2x? That would be negative 2. Don't forget to distribute that minus. So f of x could be rewritten as x plus 2 plus negative 5 over x plus 2. So when x goes to infinity or negative infinity, this part of the function goes to 0 because it's a rational function whose degree in the denominator is bigger. So this will be asymptotic to the function y equals x plus 2. I mean x minus 2. Sorry about that. So if you were to draw the graph, and we won't go through the whole thing, but I'll draw it for you. But why don't you pause and try it on your own so you can just check it. All right, so roughly like this. Negative through the x-intercept, vertical asymptote through the x-intercept, and then to the slant asymptote.